You can't escape the gravitational pull of a black hole. But another description of the event horizon, which confused people all the way through the history of black hole research actually, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops.
What if everything we know about the universe is only part of a much bigger story? A new discovery from the James Webb Space Telescope is challenging one of the most basic ideas in modern cosmology. Scientists studying how galaxies spin have found a surprising trend. The majority appear to rotate in the same direction. This goes against the long-held belief that the universe is isotropic, meaning it should appear uniform in all directions. Instead, it suggests a possible large-scale orientation, a kind of cosmic alignment, and even raises the bold idea that our universe could be the interior of a black hole. In this video, we'll dive into JWST's eye-opening observations and explore what they could mean for our understanding of space, time, and existence itself. The James Webb Space Telescope is giving us our clearest window yet into the early universe. Designed to look over 13 billion years into the past, it can observe galaxies as they were only a few hundred million years after the Big Bang. In a study led by astrophysicist Leah Shamir at Kansas State University, researchers analyzed images of 263 distant galaxies captured by James Webb. These galaxies are among the earliest ever observed, dating back to just 300 million years after the Big Bang. Here's where it gets strange. About 60% of these galaxies seem to be rotating clockwise, while only 40% spin the other way. That may not sound like a huge difference, but in cosmological terms, it's statistically significant. If the universe were truly uniform and random on large scales, we'd expect roughly equal numbers of clockwise and counterclockwise galaxies. Instead, this imbalance suggests a preferred direction in space. And this isn't the first time such a symmetry has been noticed. Previous galaxy surveys using the Hubble Space Telescope hinted at a similar spin bias, but the sample sizes were too limited to draw firm conclusions. Now, with James Webb's unprecedented detail, the pattern is harder to dismiss. Why does this matter? According to the standard model of cosmology, the early universe should have had no built-in direction. Over time, as galaxies formed and evolved, their spin directions should have averaged out. But if the early universe already had a built-in twist, then something fundamental may have shaped it before or during the Big Bang. Could there be a cosmic axis, a directional imprint woven into the fabric of space-time itself? One possible explanation goes back to an alternative theory called black hole cosmology. This idea proposes that our entire universe may be the interior of a rotating black hole in a larger parent universe. Instead of beginning with a singular Big Bang, the universe may have formed through a process known as a cosmic bounce, where a collapsing region of space doesn't end in a singularity but rebounds, giving birth to a new universe. How does this connect to the galaxy rotation findings? If our universe formed inside a spinning black hole, that spin could have influenced the overall rotation of space itself, leaving an imprint visible in how galaxies rotate. That twist, inherited from the black hole's angular momentum, could explain the imbalance observed in James Webb's data. It's like a cosmic fingerprint left behind from whatever spawned our universe. This isn't just science fiction. Physicists like Nico Popławski have developed mathematical models based on Einstein-Cartan theory, an extension of general relativity that includes the intrinsic spin of particles. In this framework, black holes don't end in singularities, but create new expanding regions of space-time, new universes. If our universe formed this way, it could help explain other puzzles in cosmology, such as the Hubble tension, the ongoing disagreement over the universe's rate of expansion. It might also account for the impossible galaxies JWST has found, massive, mature-looking galaxies forming too early to fit with standard models. If some structure survived from before the bounce, early galaxy formation could have been accelerated. Of course, these ideas remain speculative. The current rotation study is based on just 263 galaxies, a meaningful start, but not enough to declare a cosmic revolution. For this theory to gain traction, researchers need to study thousands more galaxies in different parts of the sky to see if the spin bias is truly universal. They also have to carefully rule out observational biases. Could the way we view galaxies from our position in the Milky Way be skewing the results? Or could JWST's imaging methods be unintentionally introducing this pattern? What comes next? Scientists will expand deep field surveys with JWST, collecting more data on early galaxies. They'll also look for primordial black holes or other cosmic relics that could support the bounce universe theory. And cosmologists may revisit the models used to measure cosmic distances and expansion rates, which could help resolve the discrepancies known as the Hubble tension. Whether or not we end up inside a black hole, one thing is clear. JWST is forcing us to rethink our deepest assumptions about the universe. It's pushing us toward bold questions about where we come from, how the universe really works, and whether the cosmos itself has a hidden structure guiding its evolution. So, is the universe inside a black hole? We don't know yet, but the galactic spin alignment seen in JWST's data makes it a question worth taking seriously. As new data pours in, we'll find out whether this directional bias holds and whether it points to a cosmic origin story stranger than anything we imagined. As more galaxies come into focus and more data is analyzed, we may find answers or entirely new mysteries. Stay curious, stay questioning, and keep looking up, because the universe may not be what we thought it was.